We'll start to gain a few minutes just so I can give you a few more small signal examples before we start doing the homework. So the first thing is there was some confusion about whether there is going to be a lecture on Wednesday. So this is a makeup for the Wednesday lecture. So because I'm not in town, so there will be no lecture office hours. But if people really need, kind of last minute help me on my homework or any questions, I'll move the office hours to 3 to 4 p.m. On Thursday. So these would be the Wednesday office hours. Okay, and then normally then Friday after class, everything's normal. Okay, so let's dive in kind of immediately into the topic of the lecture. We're gonna talk today about how do we use the small signal models that we defined for the MOSFET in these like single transistor amplifier configurations. So as you can imagine, just like we had common gate, common base, common emitter, common collector configurations in bipolars, now we're going to have common gate, common drain, common source type of configurations in with MOSFETs, and with some sort of variations on the topic in terms of expressions, just because here we have this GMB effect, which is the source body effect, that makes things a little bit nastier when you try deriving the full equations. Okay. So before we dive into that, I sort of wanted to talk a little bit about the biasing of the FETs, because you're going to have, that's also kind of on the homework, but just in terms of understanding the operation regions and summarizing that. So let's say we have this configuration where this is our drain and here is VO. This configuration is called common source because I've grounded the source terminal. My body terminal then is also grounded. And what I'm trying to do most of the times with these amplifiers, I have some small signal here that I'm trying to amplify to the output. So there will be some, and so this signal will have the bias point VI, and then this small signal will really be VI on top. And then as well here, we'll have the bias BVO, and then the opposite phase, this will be my VO. Right. The opposite phase is because, as you can sort of inspect from this, if I'm increasing the gate voltage, I'm kind of increasing the drain current, right? And then that drops this value over here because the larger, let's make this the real ID. The larger this ID value is, the more voltage I'm dropping across this resistor, so my VO goes down. Okay, so we say that essentially these two, there's a pi phase shift between the input and output. So it's kind of feeding an ideal amplifier at the minus terminal, right? Okay. Now, in terms of how we can realize the biasing VI for VI. So here, as an example, scheme very similar to what we did with our and then I can kind of add here a very large capacitor. I have my RS, and then I have my right. The nice thing here is that base current that we were worried about, and we're making sure that kind of the current through R1, R2 is much larger than the base current, so we can do the voltage divider. Well, now we don't have that anymore, right? There is no current flowing here in terms of the biasing. So, oops. So I gate equals 0. Notice that this is capital, right? So in terms of DC, there's no current. Of course, there is AC current, meaning there's a small signal variation current because, in the models that we had, that one, because we don't have the RG, that one is also going to be 0. But normally, if there's a little bit of a leakage, there will be kind of a fluctuation in current. So for all intents and purposes, it's easier because we can kind of disregard the current flowing into this terminal. Okay. So in this scenario, then our VGS is going to be just R2 over R1 plus R2 times VDD. Okay. So if we look at this transistor over here, we want to sort of, based on the VI and VO, we want to define, so there's 3 regions of operation. In which I can sort of bias this, this common source transistor. So one is we're going to call it cutoff. And that is for VI smaller than V threshold. So in that sense, if this input node is smaller than the threshold, obviously this transistor is off. Okay? And if it's off, the drain current is 0. There's nothing. The output voltage is VDD. Then the next one is going to be linear. And so that is for VI is greater than VTH. But we also have to look at where the VO node is. Okay? So if VO node is smaller than VI minus VTH, and so the usual inspection in the circuit is if this node is down by VTH from the gate, then you're in linear region. You've sort of pushed this transistor in the linear region. So it's like, and then the one we're really interested in working in, because it's kind of a near constant current for a given gate voltage, is the saturation region, which is kind of equivalent to the forward active of the bipolar transistor. And here we have VI is greater than threshold, so transistor is on. But we have VO is greater than VI minus VTH. So it may be a little bit confusing because saturation in the BJT case, sense was the bad region, right? And here, for MOSFETs, saturation is actually a good region. Okay. So yeah, what can we do? It's like the legacy nomenclature of the past. Okay, so maybe one more thing to add, that just in terms of homework, by simply writing out what ID is as a function of VI, you'll be able to kind of then relate to ID to the V out, and then you'll be able to kind of eliminate ID from the equation and get something that's just a function of V in and V out, and that will essentially turn into your V out as a function of V in curve. So what I've drawn here was a common source with RD as the load, which is the resistor. Homework, you have something a little bit different. That's another transistor, but it should kind of end up being very similar when you combine the equations, right? So just to give you a notion. Normally, and we'll do this a lot more when we talk about the output stages, is we can create something that's called a load line. So if you look at the ID versus VDS curve, we said that a transistor has this region that is defined by This is our ID sat curve, which is K prime over 2 W over L VGS minus VTH square. At this curve, in this curve, we also have that VDS equals VGS minus V threshold, right? That's why we can draw it on this diagram. Otherwise, we won't be able to draw something as a function of VG on an axis that's VDS, right? And so from here, we've said that, okay, well, in this region, we have nearly constant. I'm ignoring a little bit the early effect, but nearly constant current as a function of VDS. And that region is called saturation. So this is VG1, VG2, VG3. And then in triout, or in linear region, we have these lines. So this is linear region. Now, if I try to map, so this is just a single transistor. Wherever I put this transistor, it will have these characteristics. Okay? Now I can add additional curve that will tell me what operating conditions I'm imposing on that transistor by adding that load resistor. Right? So we are having this situation here. So now this is my VDS, right? And this is ID. Simply because I have this resistor, now I can relate ID and VDS, right? So my VDS is equal to VDD minus ID RD, right? So if I try to map this, so for ID of 0, I'm at VDD. And for VDS of 0, my ID is VDD over RD. Okay. So if I plot this line, well, let me use another color maybe just to... Okay. If I plot that line, this is where my output is going to move. Okay. Because, so in this whole two-dimensional space of VDS versus ID, I can only run on that line because that's set up by this RD. So as I'm changing my VG, which is my input, so I'm changing my, VI, I can only run, so from VI being 0, I start from here, and I can then only run in this direction, okay? Up until I hit this point, and then I cross into the linear region. So it's kind of useful visualization as to where you're going and how VI is related to, and ID and VDS are related, right? So you can only move on this line. Now, in terms of amplifying the signal, why is it useful to draw these like V out versus V in lines? Well, I can sort of find where I'm getting the region of the highest gain, and also how far away I am from each point, cutoff or linear region, so that I can accommodate the largest signal coming in and getting out of the stage. So if I'm drawing it on this space, I'm going to have, let's say, VTH here. So for VI smaller than VTH, I'm going to be stuck in this point. Okay, so I'm going to be at VDD. Simply because there's no current flowing, right? So my output is pinned up to VDD. And then once I start conducting, I know that I'm immediately going to be in the saturation region, right? I know from this load curve, because I can't immediately jump all the way over there. I'm slowly increasing my VN, so I'm climbing here, okay? And So I'm in this parabola region, which is defined by saturation. So by this point, it's cut off. And then here, it's saturation. And then I know there is a point here at which VI V out equals VI minus V threshold. Right. So for that point, I'm going to enter the linear region. And then I'm going to slide down. And so eventually I'll hit, I'm going to kind of come all the way up to here. And there will be more curves coming up. I'm going to hit likely where VDD is for the input. And for that current, so there will be still potentially some voltage that is defined by, in triode, my transistor looks more like a resistor. So it will be a resistive divider of that transistor and the RD. So that's why, the current is not zero. The voltage is not zero. Okay. And so if I'm looking to position myself somewhere here, I want to find the VI point. So this is going to be VI. This is my bias around which, if this is time, I want to apply my VI, which is the input signal. And then I'll be getting the V out voltage again in time. And it will be, okay, I guess we have to define this as plus and this is minus so that we can kind of be phase accurate. Maybe I don't, okay, I want to do it so that it's essentially in the region when I'm not coming into the linear region. Okay. This is just to give you a little bit of intuition what's happening and how these transfer functions are affecting the transfer of the small signal all the way to the output. You have a little bit more detailed thing in the homework where you're going to do this curve and then figure out the best point to put this on. Okay. What's the question? Is the voltage between drain and source zero? At which point? Voltage between drain and source. Well, okay, in which region? In the linear region. So in the linear region, you still have some current that's flowing through the transistor, right? So that current will be this ID. It's just now it's also dependent on VDS, right? Because it's VGS minus VTH times VDS minus VDS square over 2, right? And so, but if you look at these curves, this type of shape, is more like a resistor, right? It has, so this shape is not a resistor, it's more like a current source. This shape is more like a resistor. So that's why I said the very zero order approximation of transistor in linear region is that it's just like a resistor. So it will be dividing the voltage between its own resistance and the resistance of the load. Right? And that's kind of what happens here. Now it becomes a resistor. So you have the output voltage is the resistance of the, is basically this kind of slope, right? Divided by the sum of the two, right? Okay. Now, if you look at CMOS, sort of, if I was to kill this RD, then indeed I would pull this all the way to ground, right? But in this case, this RD is still providing some current. Okay. So let's move on to the small signal models. Let's change the color. Okay, so we're gonna again start from some very simple stuff and progressively get more complicated. So we're gonna say that there's some VI here and a small source. We're gonna add the RS. Okay. And if we take a look at something like this, when we map it to small signal, then it's going to look something like this, where this is now gate. And then on this side, we have GM VGS. This is gonna be our source. And then in the simple model, we're going, well, in this model, actually, body is also tied to ground, just like a source. So we don't have the GMB component. So this is R0. And then we have the RD in parallel. Okay. So I'm going to try now to map this to sort of equivalent amplifier models. And so let's define these amplifier models. It's kind of getting close to sort of the ideal amplifier or sort of the real but abstracted amplifier. So if I have voltage V1 and current I1, I'm developing that current on some resistance Rin that I'm going to call input resistance of the amplifier. Right? That may be infinity, but it may be something else. Okay. And then what I'm going to have here is I'm going to have capital GM times V1. And then I'm going to have some capital R out. And this will be my VO. Or in this case, I'll label it V2. And say that this is I2. So this is one way of representing it. Another way is to say this is Rn and this is V1. But on the other side, I have a voltage-controlled voltage source, which is AV times V1. And then I'm just turning this Norton equivalent into a Thevenin equivalent. So I'm going to add R out here. Okay. So here I'm going to essentially, whenever I look at the real transistor stages, in order to map this to this abstracted amplifier configuration, I need to find things like Rin, R out, these capital things, as functions of transistor small signal parameters and any biasing network around. And then also GM, and I'll define GM from here as sort of I2 divided by V1 when V2 equals 0. Right? So when V2 is shorted, I have no current going through R out, so all the current goes through GM-V1. Right? And then I'm going to define also AV is V2 over V1 for I2 equals 0. So again, if this I2 is 0, then this current is really developing V2 on this R out. But also in terms of this model, if I2 is 0, and this is I2, that just means that V2 equals AV times V1. Right? So there's no voltage developing on R out. Okay. So, okay, going back to our example over here, what can we say about the input? You know, the input resistance would be Rn. What's the input resistance? You start seeing RS, but then after RS you see something much bigger. Huh? Infinity, right? So remember, the way I'm doing this is when I say what is Rn, I'm really thinking V test over I test. So if I apply, you know, if I put a voltage source VT, there's not going to be any current because it's seeing this open from gate to source, right? So it will be, the network will be something like V test into RS into open, right? And therefore IT equals 0. So then this, you know, goes to infinity. Okay, well, let's look at AV. So that's VO over VI in our model over here. So what is that? What is VGS in terms of VI if there's no current flowing? They are the same, right? Oops. So this equals VI. And then here I'm getting GM times VI. And then all that current is going into parallel combination of these two transistors, right? So I have minus GM times what? Yep. Oops. Escapes. RO in parallel with RD. Okay. Now, let's have that there for a moment, and then now let's take a look at what is the, we're going to call this RO or R out. What is the resistance that we see from the output node in? Yep. So it's just these two are not in parallel with RD. And the reason is that when I apply a test from this side, I have to short VI. Right? So maybe that's worthwhile writing. So I have to short VI. So this is now my gate. This is now my source. And then I have here GM VGS. And then I have R0 and RD. Now notice that because VGS is 0, then GM VGS is 0. So if there's no current, so essentially I can just delete that piece, right? And then all I have is these two in parallel. So basically, this is my R out. And just by definition, If you look at the equivalence of this to that, my AV from here, AV equals minus GM R out. So if I put these two right next to one another, then GM's, the capital GM is going to be equal to small gm. That make sense? Okay, so now we've mapped sort of the parameters of the small signal parameters of this transistor into the parameters of the amplifier. So if I treated this whole thing as an amplifier, now I know how these parameters relate to one another. Okay, so if we go and look at another scheme, so now it's going to get progressively harder. So we're going to look at this topology. And then, okay, anybody has a clue what this topology is, or how is it called? Okay. Or, yep. Any guesses to what's the overall gain of this thing? Yeah, so it's sort of close. Maybe it's a little bit worse, right? So maybe a little bit more worse than what we normally have in a BJT configuration. So that's kind of the intuition, right? From what we know in BJTs, that's what we should expect. But the deriving it is a little bit more involved simply because of this issue with, okay, where is my body tied, right? And my body is not tied to source. Then I have this source body effect, right? So this is ground over here. So let's draw the small signal model and see how we can maybe apply some tricks to make this analysis easier. Now we have to explicitly call out the body terminal and try to draw it nicely here. So this is our V out. And then I have this piece over here. And then I have R naught. And then I'm AC grounding this. This is the supply, but because we're looking at small signals, a derivative of a constant is 0, right? So that's why this is grounded as well. And then also this node is grounded. This, of course, is VGS. So now when I go and I can write out what the expression for V0 is. And